Thank you so much for the invitation. Excited to be here. So let's just start with talking about moduli of K3. So we're going to consider polarized K3 surfaces, which is surface X together with the line bundle L, such that the canonical bundle of X is trivial, H1 of X is 0, and L over X is an ample line bundle. And there is a numerical invariant associated with this, which is the degree of the line bundle, which is some positive even integer to B. And so the sort of key theorem, which lets us understand the moduli of K3 surfaces, is the Torelli theorem due to it has to be 0. And proper image from around 1973. So the moduli of K3 surfaces, polarized K3 surfaces of degree 2D, is isomorphic to a locally symmetric space. So this is an arithmetic quotient of a type 4 domain, Hermitian symmetric domain. And concretely, so this D is the space of polarized Hodge structures, Z Hodge structures of type 1 of 19(1) on C1 of L per inside of the integer cohomology of the K3 surface.
All right. Don't you want to hear quasi-polarized?
Yeah. So I'm gonna so my K3 surface X, I'll allow to have 8.
No, I don't get this.
All right. Okay, so let's just give some examples. So examples. If you take the double cover of P2, branch over a sectic curve. So let's call B the branch locus. Then we get degree 2 K3 surface. Let's call this say pi, where L is pi of star of O1. And for instance, if we take X in P3 smooth quartic, which gives another example. And you can sort of easily compute that the dimension of the moduli spaces in each of these two cases is 19. And in fact, the map that assigns XL to the Hodge structure on H2 that is represented by the line H2 0 of X. Defines an isomorphism from F2D to the period limit. All right, so so let's discuss compactification. Oh, right, yeah. Okay. All right, so compactification. Of D mod gamma. So the sort of story of compactification starts with the theorem of Bailey-Burrell from 1966. says that this arithmetic quotient has sort of canonically defined compactification, has a compactification. To a projective variety. And so in particular, this d mod gamma is quasi-projective. And I want to describe what you see at the boundary of this compactification. So here's my picture of d mod gamma, some sort of blob. And at the boundary of this blob, we have 0 cusps and 1 cusps. So the 0 cusps are points, and the 1 cusps are curves. And the 0 cusps are in bijection with isotropic lines inside of the lattice L curve. Isotropic lines, isotropic for the natural quadratic form, which is the intersection pairing.
You really want to call it that? L?
It's L per, the polarization. L is the polarization, and then taking the perp of L, yeah, in H2. And J, the 1 cusps correspond to isotropic planes. And these are in fact the only isotropic subspaces because, you know, L squared is positive, and the signature of the intersection form on H2 of the K3 surface is 319. So these imply that the signature of L perp is 219, and so 2 is an upper bound for the rank of an isotropic sublattice. So you should think of this as in analogy with, say, when you take the moduli space of elliptic curves, which is like H mod SL2Z, you add the rational points at the boundary, the rational cusps, and then you quotient to get, you know, the P1, the J line, you know, P1. So somehow you're kind of doing the same thing here. You add rational, the so-called rational boundary components to D, and then with a horrible topology, and you quotient by gamma to get this compactification. All right, so this is this gives a compactification, but let's sort of observe that this boundary, the boundary has high codimension. Because so for moduli of K3s, you know, d mod gamma is 19-dimensional, but this is only 1 and 0-dimensional components. So I want to discuss the toroidal compactifications. So these are sort of Goethe Mumford and his collaborators at before time. So there exists a class of compactifications. Let me write it as d mod gamma bar f, depending on certain combinatorial data. Of a fan. So let me describe this combinatorial data. This is how you know, this sort of first part of the story about compactification of d mod gamma, it doesn't really have anything to do with K3 surfaces, right? It's just I mean, it's just a compactification, you know, a way to compactify these arithmetic quotients of symmetric spaces. And so that was sort of it's a priori, it doesn't really have anything to do with K3 surfaces, but our goal is going to be to try to kind of relate, the geometry of degenerating K3 surfaces to these toroidal and other types of compactifications. So let me what is this data F? So it's a collection of F sub I, where I is really strictly speaking a gamma orbit of isotropic line. And if I look at the lattice I perp mod I, okay, so I is a sublattice of L perp. So then the positive and negative signature will decrease by 1. So the signature of this lattice is 118. And so we can think of what we have is a rank 19 lattice with a Lorentzian signature intersection form. So we can consider the positive cone consisting of a connected component of the positive norm vectors. And now, one model for hyperbolic space is the projectivization of this positive cone, right? So real hyperbolic space, instrument 18, is the projectivization of this positive cone. And so the combinatorial data that you need to define one of these toroidal compactifications is a tiling of this hyperbolic space. Okay, so let me draw. Here's my toy picture. I can't draw H18, so I'll draw H2. And we take some sort of so the data of this F sub I is a stabilizer in gamma of I invariant. Say it's like a periodic rational polyhedral tiling. And the sort of advantage of these toroidal compactifications is that, okay, so now this blob is not hyperbolic space, but D mod gamma again. So if I take sort of the points, those sort of maximal cells of this tiling, those correspond to the deepest strata of the boundary. If I take, say, a codimension 1 cell, that corresponds to a C star in the boundary. And more generally, we get some union of toric varieties of the boundary, whose combinatorics is encoded by this polyhedral tiling. So we get some sort of complicated mess of toric varieties. And then let me draw maybe yellow. We have these other boundary divisors that correspond to the 1 cusps. They fiber over the 1 cusps of the Bailey Burrow compactification. So these divisors that fiber over the 1 cusps correspond to the cusps of the hyperbolic space. Okay.
This condition about stabilizer invariant means that there's going to be compatibility on the 1-dimensional cusp is automatic.
Yeah. So okay. So the stabilizer of gamma invariantness is because what you're going to do is, I mean, this tiling gives a fan in this positive cone. So you take the toric variety of this fan, but that's some infinite type toric variety. And then you have to quotient that infinite type toric variety by this infinite arithmetic subgroup of O118. And then when you quotient, that will locally model the boundary. So this sort of dual intersection complex of this blob of toric varieties will be the hyperbolic orbitals like HAT mod this group. And right, so we get these very nice compactifications. For instance, the boundary is divisorial instead of being, very high codimension. And the singularities of the boundary are pretty nice. You have, finite quotients of toric singularities at the boundary. So for the purposes of, say, if you wanted to, do intersection theory on moduli spaces of K3 surfaces, one thing you might want to do is, consider nice compactification with mild singularities at the boundary for which you can sort of compute the intersection theory in some reasonable way. All right, and then I do want to just mention one more sort of unifying the Bailey-Burrell and toroidal pictures. So this is work of Loyenka from 84, is that is the notion of a semi-toroidal compactification. So this is where we allow this F to be only locally rational polyhedral. And so, for example, the Bailey-Burrell compactification is in fact a semi-toroidal compactification associated to the polyhedral decomposition of the cone C+, which is just the entire cone. So this gives some natural class of compactifications, but the question is, what's the geometric meaning of, is there some geometric meaning to any of them? So now let me discuss geometric compactifications. All right, so I want you guys to take a leap of faith and assume the following theorem due to Polar, Pepper-Barron, and Alexeyev. So this is from 88 and from 96. So the moduli spaces of SLP stable pairs are proper. Okay, so I have to tell you what are SLP stable pairs? Okay, so a pair of XD, where X is the projective variety and D is the divisor, is a SLP stable pair. Sorry, let me specify a Q divisor. Is SLP stable if the following two conditions hold? First, the canonical bundle plus D is Q Cartier and ample. And second, that the pair XD has mild, I won't get too much into, but the correct notion of mild is SLC singularities. And so instead of giving a general definition, let me give some specific examples of SLC stable pairs. So for instance, if X is a curve and D is a sum of points, then XD is SLC and stable if and only if XD is in some MDM bar. So somehow knowing this theorem in the abstract, we can construct a compactification of MGN, right? Which is that we take all smooth curves with a divisor, which is the sum of distinct points, and we just take the closure in the moduli space of SLC stable pairs. So since these moduli spaces are proper, we know that we get some compactification of MGN. And in fact, the compactification that we get is MGN bar.
So do you want like maybe the weights on the endpoints, whether you're fractional?
No, I want the points to be weight 1. To get MGN bar, I should put weights 1.
But in general, you could.
But then you could vary, and then you would get like acid moduli spaces and other things like that. So in some sense, these moduli spaces of stable SLC pairs are the natural generalization of MGN bar to all dimensions.
Effective on one point, or should we introduce it? Like, when
Yeah, effective, yeah. I really mean a sum of distinct points. Yeah. So, there's obviously an issue with using this to compactify the moduli of K3 surfaces, right? Because the canonical bundle of a K3 surface is trivial, right? So if X is a K3, you can't take the divisor D to be empty, right? Because then KX plus D won't be ample, right? All right, so this leads to, so if you want to apply this theory, you somehow need to choose an ample divisor on at least the generic K3 surface. So this is what I'll call a universal choice of polarizing divisor on the moduli space F2D is nothing more than a divisor, let me call it R, on the universal K3 surface. So it's, say, the K3 surface. Okay, let's say over the function field. So it's the K3 surface over the generic point of the moduli space. There's a divisor. Necessarily, it's going to be in some multiple of polarization. Okay. And now we can define a compactification. Well, okay. So yeah, maybe let's observe that there exists then a family of pairs. Maybe I'll call it curly X their family, X star, R star, over some open set U in F2D through the open. And now let me define compact, proper space F2DR to be the closure of the space of pairs X epsilon R, where X represents a point in the open set U. So I take the set of such pairs and I just take the closure in the space of SLC stable pairs. Okay, so a priori, this isn't even a compactification of F2D because it only contains the open set U, so it's a compactification of the open set U.
And depends on epsilon, right?
Yes, okay, great, thank you. I forgot I was gonna say. So it's important to note that, yeah, so first of all, that Kx plus epsilon R is ample for any positive epsilon, because we've tipped it just slightly, you know, in the ample direction from the trivial bundle. And then for all epsilon sufficiently small, this has SLC singularity. So somehow this SLC condition is about, you know, certain discrepancies for resolutions, and so taking epsilon small enough, we wash away all those issues. And then the third remark is that this moduli space is actually the same for all sufficiently small epsilon. So it sort of stabilizes and is just one moduli space if you take epsilon less than, you know, 1/1,000,000,000. Okay, where a trillion depends on L squared. Okay, so we have a compactification, and the nice thing about it is that it has a universal family, right? There's a universal family of stable SLC pairs. I'll just use notation and still call it, I called it star first. A universal family over this F2D on. But one question you could ask is, well, like, can we expect this moduli space, this compactification, have any nice properties? Because, like, for instance, you know, there's like a theorem of Hiels, who says that if you consider general type surfaces, moduli of general type surfaces, then they satisfy Murphy's law. So you get arbitrarily bad singularities. So if this, you know, and what we're doing is we're sort of making the K3 into something log general type. And so you could imagine that maybe Murphy's law would still hold, in which case the connection with the previous section about toroidal singularities, that would be impossible, right? Okay,
So to what extent will this be independent of R? Or is there any feature of the moduli space that will be independent of the choice of R?
yeah, well, that's a, okay, so one thing is that it always maps to the Bailey-Drell compactification, but we're gonna see that in fact, you know, there is a dependency on R, but you can get a nice compactification, a geometrically nice one, you know, like with mild singularities of the boundary, for the appropriate choices of R at least. So this Murphy's law does not in fact hold in this case. Yeah.
You said it contains Bailey Borel. A priori, it's not even clear that it contains FP.
Yeah, absolutely. So yeah, we have to. Okay, we're going to have to restrict our choices of R to something a little bit more reasonable than just an arbitrary divisor. Okay. Yeah. So the
And also, do you have some sense of what you're throwing out? That's not.
no, yeah. So okay, yeah. So it will contain F2D if it satisfies this reasonable condition. So we'll see what the reasonable condition is in a second. Right. So let's not leap to any conclusions about the singularities that will appear on the moduli space. All right, so let's do some examples of such a universal choice of polarizing divisor. Well, we said that degree 2 K3s were given by 2-to-1 branch covers over P2 branched over a sextet. And this is something that is canonically associated just with the polarized K3, because this morphism is just the linear system of L. And there's the ramification divisor of this map, which gives a divisor on any degree 2 K3 surface. So then this is such a choice. So ramification, R equals the ramification divisor. Give us an example. Let me. One more example here. So let me consider elliptic K3. So that's a lattice polarized moduli space. So let's ignore that for the moment. But So these are elliptic vibrations of the K3 surface over P1 with section S, okay? And now I can take as my divisor R the section plus the sum from I equals 1 to 24 of the singular fibers. So there's always counted with multiplicity, 24 singular fibers of the elliptic K3 surface. So it's you know, it only, this divisor you kind of get for free just from the fact that you have an elliptic K3 surface. And now let me give an example in all degrees. Okay, actually, while I erase, can anyone think of an example in all degrees?
I mean, R stands for rational, doesn't it?
Yeah, that's okay. That's right. Yeah. Okay, so what's your example?
I mean, you gave us the clue, the R, the rational.
Yeah.
You should have picked a different letter if you wanted.
Yeah. R was for ramification. Because the first paper we wrote on this was the degree 2 one. That's right. So for a general degree 2D, we can take RC, the rational curves divisor, to be the sum over all terms in the linear system of the primitive polarization, such that CI is rational of C. CI. Okay, so strictly speaking, I should really define this one only over the generic point of moduli space. So, because otherwise there's, you know, some complicated questions concerning what multiplicities I should take on the rational curves.
Well,
So the answer is not hard. It's like the integral of the reduced chroma with invariant over the curves that have that image. So this is in some multiple n sub dl, where n sub d by the GAUS formula is famously given as the q to the d coefficient of 1 over the modulated discriminant, the unique weight 12 cusp form.
So all the examples are like kind of high multiples of L. Is there something that's
Well, yeah, okay. I think that for a sufficiently low multiple of L, you probably won't have a section of this projective bundle over the universe of K3. But the degree 2 one's not bad. It's in 3L.
Yeah.
Okay. And this degree 2 one, it actually generalizes to all degrees. There's this flex divisor. But the flex divisor actually loses to the rational curves divisor past genus 10 or something. So the smallest one we know for big genus is this rational curves divisor.
But it's much easier to understand on the other hand. Yeah, this is a
Yeah, this is a concrete.
no, the other one.
Oh, the other one. Oh, I see. The flex divisor. Yeah. I suppose. I don't know. That's true. That's definitely true in degree 2, where, you know, having 324 bitangents of the sextic to deal with would be a painful thing. All right. Okay, so let me sort of state the main theorem. So the theorem is that this compactification that we get by considering SLC stable pairs, at least up to normalization, it's one of these semi-toroidal compactifications that's determined by that combinatorial data of a fan. Okay, so F to the F sub R for a unique semi-fan. So that's because of the locally polyhedral F sub R, when R, this divisor, is recognizable. Okay, so this is kind of the key concept for the talk. It will take a minute to define. So let me pause, let me just say, for the moment that there is a condition on R, my universal choice was polarizing divisor, which will ensure that I get one of these sort of combinatorially defined hypotheoretic magnifications. And furthermore, R equals RRC, the rational curve divisor, is recognizable.
What about if you take rational curves in 2L?
Yeah,
That's also recognizable?
that's right. Yeah.
And will the convectivations be the same then or not?
No, it'll get finer and finer. We don't even know what the semifan is for degree 2. Like it's
Do you have an R that gets you Bailey-Burrell?
no. That also is an interesting question for sure.
And the flex is recognizable or not?
If what?
The flex divisor. that you-
It's not known.
It's
So
not known.
so we've conjectured that every constant cycle curve is recognizable, and the flex divisor is constant cycle, but we haven't been able to prove that yet, that conjecture.
Mhm.
So somehow it's easy to show at least that the flex divisor extends. Okay, well, we'll see when we see the definition of recognizable.
And maybe the other direction, so in the extremo Bailey-Burrell,
Yeah,
you're asking the question if I want to get something smooth, or can I get sort of very, very fine bands? Can I achieve them, or?
yeah, so I mean, it varies, depending on the divisor. Usually the bigger the divisor is, the finer the fan, in some sense. And so, so for instance, for the, this one, for elliptic K3s, the fan is very nice. So it's toroidal, there are like 6 maximal cones in the fan. And then for these ramification divisors, it's also pretty nice, but sometimes it's a semi-fan. There's really infinite polyhedral chambers of this style. And we just don't know for the rational curve divisor. Yeah.
And
Okay.
Can you show something that if you make the divisor arbitrary, like big, then
That it's cofinal in the post set of fans or something, or
yeah, or that you can make it toroidal at least?
no, we don't know. We don't know. I mean, somehow, well, we know for elliptic K3s that it's toroidal. And then there's a paper, so there's a paper with Alexander about K3s with involution. So there's 75 moduli spaces of K3s with a non-symplectic involution, and you can take the fixed locus of the involution, and I think it's like toroidal for like, I don't know, 20 of the 50 or something, 20, I don't know. Some number of them.
So how about the symplectic involution?
Yeah, but then the fixed locus doesn't have a curve in it, so we need a divisor.
The divisor never.
We need a divisor, yeah. Okay, so what is this condition? Okay, so I want to go back to a theorem, do the Kulikov and Kurtz-Pankow. From the 70s, late 70s. So let's let X star over delta star be a degeneration of K3s over a punctured dip. Delta star containing the delta. Then after a finite phase change, we can extends to as an X over delta. So we can fill in over the central fiber such that yeah. I don't know if room for conditions. So space is smooth. Second, the canonical bundle of the total space is trivial. And third, the central fiber is simple normal crossings. All right, so somehow Mumford's semi-stable reduction theorem tells me that for any degeneration I can achieve 1 and 3, right? The minimal model program says that I can achieve 2. I can find a degeneration trivial canonical bundle. The sort of power of the theorem is that I can achieve both of these conditions at the same time. Particular to the sort of K3 and abelian surface case, and is actually false. This is false for Enriques surfaces. So if you look at Kulikov's paper, where he proves this theorem for Enriques surfaces, that is incorrect proof. I forgot. I'm being recorded.
That's right.
You don't have to sign the form.
Okay, so all right, so this is a Kulikov, and let me call the central fiber is a Kulikov surface. Okay. So now let me sort of give this key definition of recognizable divisors. We say that R is recognizable if it extends, and the keyword here is going to be uniquely, to any Kulikov surface.
Do you recall the definition of a Kulikov surface?
Oh, it's the central fiber of a Kulikov model. Okay, so I mean, let me draw a picture. Yeah, that's not very helpful. I'm sorry. Okay, so you should think in your head of something kind of like this. So you have, you have some components like V1, V2. These are like smooth surfaces, is it's S and C, and then there are sort of double curves, which are smooth curves, right? Where like you glue 2 of the surfaces, and then there are these triple points, right? Where 3 of the surfaces meet. And then furthermore, the dualizing sheaf of this should be trivial. So that's the, and then what that concretely means is that at least over 0 test that all the components are rational, and that the double locus is an anti-canonical divisor. It's a wheel of P1s, which is an anti-canonical cycle on the rational surface. So think of like P2 with a triangle of lines as a component.
So is it also unique for extended error functions?
So the Kulikov models are highly non-unique. So somehow, if you had uniqueness for Kulikov models, presumably then, the moduli space of Kulikov surfaces would be the compactification that you want. Because that would satisfy, the valuative criterion for properness for the moduli space, if they were unique. But the issue is exactly that they're not unique. And so let me say what types of additional structures we can put on these Kulikov models. So if we have a X star, L star, so now we have a polarized family over delta star, and we want to extend the line bundle, so then there exists an extension such that L is relatively nap. So this is a theorem due to Shepard-Barron in 1983. And now in our setting, we've chosen our universal choice of divisor, right? So we also want some version of the Kulikov theorem where we have a divisor. And so yeah, let me call this like maybe a Neff model. And then if I have X star, R star, where now these are really Neff divisors instead of just Neff line bundles over the punctured disk, then I can extend it to XR over the disk. such that R is relatively nap. So that's the first condition, and furthermore, this R naught contains no strata of the singular stratification of the central fiber. So the picture is sort of like, here's my picture, like the divisor I could think of as, you know, living inside these components. So it breaks up into curves on each component, but the key point is that it doesn't contain any of these double curves, and it doesn't pass through any of these triple points. And furthermore, it's still nap. And now the sort of general, so this is what one would call a log minimal model for the sort of pair. And so from it, we can actually compute the unique stable SLC limit in this magnification, the KSBA magnification. So let me just say how do you do that.
So can I ask for this? You could consider a moduli space of Kulikov surfaces, and it would, so to speak, be proper but not separated.
Yeah, it would be complete because yeah, that's right. It would be complete with respect. It satisfies the value of the criterion for completeness. Yeah,
But only from maps from the, only for limits from the interior, right?
that's right. Yeah,
Oh, if you have limits of Kulikov surfaces, they can get out of being Kulikov.
that's right. Yeah,
That's good.
yeah. It's pretty wild. Yeah. In fact, there's a moduli space of Kulikov surfaces, and it's even a smooth complex manifold, just not of finite type. Follows from deformation theory.
What's the logic on the top blackboard? So the Trevor-Barron theorem says that it's for any family that exists in the extension of the line bottom. And now for the divisor, that's the conditional that.
Sorry, there exists such an XR, and I forgot to put the citation. This is due to Laza, 16.
No condition on R for the.
It has to be relatively nap on the generic fiber, big and nap, yeah. So, I mean, there's a lot of wiggle room in these Kulikov models, and the point is that, I mean, the way the minimal model program works is that, like, take some extension, it's not nap, but you do a sequence of flops and then you make it nap. Okay, so finally, let me say the stable model. Finally, the unique SLT stable limit is x bar epsilon r bar, which is prod over the disk of the sum of the sectors of the multiples of this r. And this is for any divisor model. Okay, this is what I wrote over there. This is okay. So it gives a method to compute, you know, the unique SLC stable limit.
And you know that's finitely generated.
Yeah, so in this case you do because, yeah, so I mean somehow it's you know, finite generation of the canonical ring, the log canonical ring in this setting for it. And it's easier in this case anyway, actually, because it's surfaces. But yeah, there's definitely something to sort of, you have to justify that.
In the definition of recognizable, do you mean that for any one parameter degeneration, you can fill in the central fiber somehow?
Great, yeah, so this is a great question. So we look at our X naught, right? And we have this triangulated thing, and we have some divisor R naught, which I guess I was using a red for. Okay, and then inside it I have this R naught. And then the key point is that for any smoothing, so for any smoothing, this R naught is the flat limit of RT. So I mean, we have the divisor on the generic fiber, and what we're saying is that there's a divisor R naught, which is the limit of the RTs, no matter how I smooth X naught. That's why we call it recognizable. It's like that the Kulikov surface, from its bare geometry alone, knows what R naught should be.
But it might not have an R naught if you take the wrong one.
It might not have what?
The X0 might not have an R naught if you take the wrong one.
Well, no, it's okay. It always has, I mean, there's always the flat, for any like degeneration, you can always just take the flat limit by taking this risky closure and intersecting with the central fiber. But the key point is that that R naught that you get by taking the limit is independent of how you smooth X naught. That's the key point.
Sorry for asking that.
Yeah, sure, no
Can you
problem.
give us a normal example? Can you
Uh,
give us a Kulikov surface and a
Yeah, so here's an example. Like, let's take the push forward of L and projectivize it. So this is some sort of PG bundle. I mean, this is a dumb example, I'm sorry. I'm already apologizing, this is a stupid example, but okay, so we get some projective bundle over F2D. We just take a rational section which isn't regular. Okay, just take a rational section, take R to be a rational section, which is not regular. Then, like at the locus in F2D where the section isn't regular, this divisor R naught, there won't be a unique limit as I deform it into the other K3s. Okay, like that's sort of, if there was, then then the section would extend over that point with that value of that in the projective bundle. Does that make sense? Okay.
Hey, Phil,
No,
so
so-
does that mean that when, if you took a divisor that wasn't recognizable, that somehow you should be changing FD? That you should look,
Yeah, you might have to blow the interior even,
Yeah.
if you choose such a non-recognizable
So
divisor.
I don't,
But then I think that maybe Murphy's law will probably hold.
so I don't understand this example, because if for any choice of R, it's gonna be in some push forward of L to the N, yeah? And
Yeah,
why
that's
can't you
right.
do the
It's a
same?
section, it
Yeah,
doesn't
but
match
it's
the section.
rational and non-regular,
But these rational curve divisors, you can prove that they're recognizable by looking at the log Gromov theory of the central. crust.
Absolutely, yeah, that's right, yeah. The key point is that the image of an invisible stable genus zero map, even to a Kulikov surface, is a rigid curve.
That's the point.
So, okay, so since I sort of summarized just in words the proof that the rational curve divisor is recognizable, now let me talk a little bit about like how do you actually compute? I mean, how can you try to compute the semi-fan FR? I mean, that's the sort of question that for practical purposes, if you want to like do intersection theory on some moduli spaces, you need some explicit fans. So how to compute this fan? All right. So I guess in this talk, we're largely going to leap over the Enriques case. So I'm sorry about that. Okay, so the key sort of proposition or theorem from this paper with Valeri is that there exists a well-defined stratum function so it's let's call it bold S. So it's going to go from the positive cone in that hyperbolic lattice that you've probably forgotten about by now to the set of combinatorial types. Of SLC surfaces, like X naught, maybe bar, X like Y naught bar. And the fan the fan f sub r is the loci on which this function is locally constant. So f sub r is given by the sort of loci on which s leads. Okay, so sort of concretely, how does this work? So let's suppose that I have a vector lambda. Oh, sorry, I should take this off. Okay, suppose I have a lambda. So remember, this was in the I per mod I, the isotropic space in the purpose of polarization. And then what I do is I take a lambda and I map it to the sort of type of x naught bar epsilon r naught bar for any degeneration whose Picard left set transform corresponds to lambda. So the sort of key points that about toroidal compactifications you need here is that the integer points of this lattice are they're the co-character lattice in the toroidal compactification. So co-character is like a C star, and so it gives a degeneration of K3s. And in some sense, like these, not in some sense, these lambdas give you, they give you a formula for the Picard-Lefschetz transform on H2 of the degenerating family K3 surfaces. And somehow the key point of this recognizability is that it implies the well-definedness of this function. And so from that, you can extract the fan. And so some examples. So doing work with Thompson, we did the degree 2 case that we discussed the example of. So that ended up being a recognizable divisor with Brugnete. We did the elliptic K3s. And then in another paper, we did the fixed locus of iota, where iota is a non-symplectic involution. And I guess I'm mostly out of time here, but there's a very beautiful combinatorics, like the sort of hyperbolic lattices in sort of at least in all of these cases, the hyperbolic lattices end up being hyperbolic group lattices. So there's a fan, which is like the Coxeter chamber for all the reflections. And then you get a hyperbolic reflection group. So you get a tiling of the hyperbolic space by taking the positive chamber for the roots and successively reflecting it across all of the walls. So you get some reflection semifan. And it's really this reflection semifan that in these cases is relevant. So in this case, it's a refinement of the reflection fan, and in these cases, it's a coarsening of the reflection fan. And yeah, like they're interesting moduli spaces. There's lots of, so like for instance, this one has like over 2 million boundary strata and 38 boundary divisors. Like there's a lot of interesting geometry. So I guess I'll stop there. Thanks.